Hey everybody, in this video we're going to talk about the standard normal curve, and we're also going to look at some normal curves that have some values that are attached to it as well. So the first part of this video, the standard normal curve, we're looking at this notation here. Z is approximately, or that squiggle, N01. So what does all of this mean? Well, the Z represents Z-scores, and the Z-scores are really any given standard deviation on a normal curve. So yeah, just basically that, any given standard deviation on the normal curve at some place along that line. N means that it's normally distributed. The 0 is our mean, or we use the symbol mu. And the 1 here is our variance, which is our standard deviation squared, or in this case we can just consider it the standard deviation because the square root of the variance is going to be 1, standard deviation squared is 1. All those values are all basically equal, so we don't have to distinguish one from the other, so we can just call it standard deviation or variance. Now, what does all of this mean? When do we use this? When does this apply, this notation? And this is really used when we know that the data is normally distributed. So maybe we're told that in one way, shape, or form, but we don't know what the values of the mean and the standard deviation are, or the mean and the variance. So we have no idea what those values are, but we do know that the data is normally distributed. Alright, so let's look at a curve. So if we plug in our values, or if we label it as we normally do, we normally put the mean in the middle, and then we count up our standard deviations on the right, count down our standard deviations on the left. We have a nice number line here representing our standard deviations. With the standard normal curve and this Z notation, our mean here is 0, or we're assuming our mean to be 0 because we don't know what the values for the mean and standard deviation are. In a previous video we talked about how it doesn't matter where these things are placed along any kind of number line, because as long as we are comparing them within or in reference to standard deviations, that we don't need to know what the specific values are to find placement values along that continuum of standard deviations. So in this case, we're just assuming the mean to be 0 and the standard deviations to be 1, so we can label them as 1, 2, 3 standard deviations, negative 1, 2, 3, and this whole thing is considered the z-scores. You notice that obviously the values and the number of standard deviations that we're talking about line up. 1 standard deviation above the mean is the value of 1. 2 standard deviations above the mean is 2. So that's why when we're using this standard normal curve and we're assuming the mean and the standard deviation to be 0 and 1, it's kind of interchangeable with the idea that these things are the standard deviations. So the z-scores are the standard deviations. Okay, so let's look at an example or two and see how this can apply. So the probability that the z-score is less than 0. So we're basically looking for this space. Well, we know also from previous videos that this is cut in half at the mean, so this is going to be 0.5. Probability is going to be 50%. What about if we had the probability that the z-score is less than 1? Okay, so now we're looking for this orange piece as well as the blue piece. So we already know up to the mean is 50%, from the left up to the mean is 50%. And we know that between negative 1 and 1 standard deviation is roughly 68% of the data. So that means that 34% is from the mean to the first standard deviation. So we can add these two values, 0.5 and 0.34, and we get a value of 0.84. Alright, let's make this a little bit more complicated. What about the probability that the z-score falls between negative 2 and 1? Alright, so we've got our curve again, we've got our z-scores labeled on here. So we are looking for negative 2 to 1. Alright, so if we consider the middle at our mean, we know that this value is 0.34. 0.34, we just found that in the previous. and we know we can find this value. Now this, remember that between -2 and 2 standard deviations is approximately 95% of all of the data in the curve. So we want to look for half of that 0.95, or that 95%, because we're looking just from the mean down to -2. So if we calculate that, we'll get a 0.7475, add those two values together, and we get 0.815, or a probability of 81.5%. Now, a nice thing that we have is also on our calculators, there's a function called normal CDF. And the normal CDF, we had to input 4 values, and it will give us this whole shaded region that we just found in the purple here. So what it looks for is the lower bound, then it wants the upper bound, the mean, and the standard deviation. So in this case, the lower bound, the lower end of the range of data that, or the range of the probabilities that we're looking for, is going to be -2. So we would put into our function, our normal CDF function in the calculator, we put -2. Our upper bound is going to be 1. That's where we want to stop looking. So we got 1. Our mean, well, up here we said our mean is 0, so we'll just put in 0. And our standard deviation, well, up here our variance is 1 squared, or our standard deviation squared, which is 1. So we put in 1 there. So that's a standard deviation value. That's not the variance value. This is where it can get kind of tricky. For some unknown reason, to me anyway, the notation uses the variance, but the calculators use the standard deviation. So you got to make sure that you are switching those up when you're looking at those. That if you're using that notation, the z is approximately normally distributed with a 0 or 1. That you're taking the square root of that variance. So again, in this case, square root of 1 is 1, so we're good to go. Anyway, if we were to punch this into our calculator, we would get a value of 0.819. And this is the actual probability of the z-score falling between -2 and 1. Now you're probably saying, wait a minute, we just said that this was 0.815. Now remember, when we talk about 68% of the data between 1 standard deviation and 95% of the data between 2 standard deviations, those are approximations. So just to give a rough estimate, we can use those values, but as we get more and more specific, we'll want to use this normal CDF function. For example, let's look at one more curve, and let's look at the probability that z is greater than -1.5. Okay, so we are looking from here on up. So this was not one of those standard assumed percentages or standard deviations that we looked at. So we have to use something with our normal CDF. Because we don't know exactly what percentage falls at -1.5. You know, we can make an assumption that it's halfway between 34 and 47.5, and that'd probably be a pretty safe assumption. But you know, let's be a little bit more precise. Let's use that normal CDF function. So normal CDF, first thing we have to do is our lower bound. And our lower bound here is -1.5, so that's the lowest value that we're looking for. The upper bound is everything on the right side of -1 up to infinity, whatever that value is. So you just put in a large number. In your calculator, you could put 1 to the exponent. I'm sorry, it's 1 to 10 to the 99th power. Sorry, I'm having a hard time saying that. Or basically, all you have to do is put a really big number. You could put in 10 million, and that will work as well. It's just a really big number outside of the range of your data that you're looking at. And here our data is looking up to 3. So any big number, 100, 200, 300, 1,000, that will all work. Then we want the mean, which again is 0, the standard deviation, which is 1, and when we punch that in, we get a value of 0.933. Okay, so that's how we can use our standard normal curves. Now, let's look at some where we've got normal distributions with some values plugged in. So now this notation is just ever so slightly different. Now we're saying we've got x as some random variable that is normally distributed with a mean and a variance. So in this case, let's label up our axes here, our mean and our standard deviations. And let's say we have a mean of 10 and a variance of 2 squared. So this means our mu is 10, our standard deviation is 2, so not 4, right? The variance is the standard deviation squared, so we take the square root of that, got our 2. So what we want to do if we're given this value is I always plug in the values kind of mirroring the standard deviations. So I've got 10 for my mean, my standard deviation is 2, so I just increase by 2 as I go up, and I decrease by 2 as I go down. Now what this little drawing that I've done here is showing us, these are the z-scores, so any standard deviation on the curve, these are the values for x that we could have. So let's look at the probability that x falls between 9.1 and 10.3. So we're looking between here. So we don't know what these values are, but we can again go to our normal CDF and we can find this. So we start with our lower bound, which is 9.1. We go to our upper bound, which is 10.3. Our mean is 10, and our standard deviation is 2, and we can calculate and get a 0.233. So this works because we have actual data values here and an actual mean and standard deviation. But what happens if we want to know what standard deviations or what z-scores do these values associate with, or do they represent? So now we don't want to look at 9.1 and 10.3. We want to know what standard deviations those represent. Okay, so there's a kind of a handy formula that we can use, and it's the z-score formula, or that's what I call it anyway. And z is equal to x minus mu divided by standard deviation. So it's a very straightforward formula that you can just plug in values and solve for the unknowns. In this case, we're trying to find the standard deviations, or the z-scores, that are represented by x being 9.1 or 10.3 with a mean of 10 and a standard deviation of 2. So all we have to do is plug these values in. 9.1 minus 10 divided by 2. So we get z divided is equal to negative 0.9 divided by 2, and in this case z-score is negative 0.45. And that's going to be our lower bound now. Our z-score for our upper bound, 10.3 minus 10 divided by 2, so we get 0.3 divided by 2, or 0.15. That would be our upper bound if we were using a normal CDF with a standard curve. So let's see how that works here. So we've got our lower bound, we've got our upper bound. So that means here at this line, at this portion of the curve, we have a standard deviation of negative 0.45, and we have an x value of 9.1. And here on the upper bound, we have a standard deviation of 0.15, and we have a 10.3 for our x value. And I say standard deviation, but I really mean z-scores for this negative 0.45 and the 0.15. We call them standard deviations because that's what they are, but they represent the z-scores. So don't think that the value of the standard deviation is changing. This is just what placement 9.1 is correlates to within the standard deviation range. So both of those things are your z-score or your x value, right? So that's what that means. So if we do our normal CDF, if we use negative 0.45 for the lower bound and we use 0.15 for our upper bound, we would have to use our mean and our standard deviation that corresponds to using z-scores, which is what we talked about at the beginning of the video. That's going to be where we've got 0 for our mean and 1 for our standard deviation. So, well, let's work through this, and then I'll kind of do a summary here. So this is the z-scores, this is the standard from the standard normal distribution, and we get the same value, 0.233, if you punch that into your calculator. Confirm that, let me know, make sure I didn't make a mistake. So what's the big deal here? The big deal is understanding that these two things can be interchangeable if you have not interchangeable, but they have corresponding values. Your z-scores and your x values all have corresponding values along the entire continuum of your normal curve. So that's really important to think about, and it's also important to think about which formula am I using. Am I going to use the mean and standard deviation being 0 and 1, or am I going to use the mean and the standard deviation being the given values for a particular problem? So you have to make sure that you keep all of that straight. The other thing to keep in mind, as I said, is keeping those straight, and this other formula, z equals x minus mu divided by standard deviation. So what I really want, I can't stress this enough, and this is where a lot of people get confused, is that each individual z-score has a corresponding value for x. Sometimes we know only the z-scores, like in the first part of this video. Sometimes we know the x values, and we don't need to know the z-scores, but we can still find them using this z equals x minus mu divided by standard deviation. So we can bounce back and forth. We've got two different methods to use our normal CDF, either using the given mean and standard deviation or using an assumed mean and standard deviation of 0 and 1. So it's a lot to take in, but I hope this helps kind of clarify how we can use the normal distributions and the standard deviations, or standard distributions, standard normal distributions, for finding various values and percentages and probabilities. So that's it for this video, and I'll talk to you in the next video.